Hey guys, I'm going to do some rotational kinematics problems for you. It's easier to do them on the smartboard where I don't have to type in the Greek letters. So it says a centrifuge rotor is accelerated for 30 seconds to 20,000 revolutions per minute. What is the average angular acceleration? Through how many revolutions has the rotor turned, assuming constant acceleration? And again, the main thing to remember is that you can only do constant acceleration problems. So the first thing I'm going to do is I'm going to convert 20,000 revolutions per minute to radians per second. And you might ask why we have all these things in revolutions per minute. It turns out that revolutions per minute is very common in describing how motors are turning. If you were to buy a drill, or if you were to buy something that mixed things, they would tell you how many revolutions per minute you would get on it. They wouldn't give you how many radians per second, but we use radians per second. So this is going to be our final angular velocity. Our initial angular velocity is 0. We don't know our acceleration, but we do know our time. So I'm going to look at the v equals v naught plus at equation, which is going to be my omega equals omega naught plus alpha t equation. And I'm going to solve for alpha. I'm going to subtract omega naught from each side and divide by t. And so this is going to give me 2,094 radians per second minus 0 over 30. So this is going to give me my acceleration. So it looks like it's about 70. So I can put that in here. And then it says, how many revolutions has the rotor turned, assuming the constant acceleration? So for this one, I'm going to have to get the radians first, and then I'm going to have to convert it back to revolutions. So I know that theta minus theta naught equals omega t plus 1/2 alpha t squared. And that's 0. So really, I'm just going to have 1/2 70 times 30 squared. So I have 31,500 radians, and then I'm going to convert this back to revolutions. And so radians are on the top here. I'm going to want to cancel them on the bottom. And there are 2 pi radians in 1 revolution. So I'm just going to divide this by 2 and divide it by pi. And I got 5,013 revolutions. I'm going to clear the ink, and I'm going to go to the next slide. And going to the next slide, you can see that I have the work done there. All right, a cooling fan is turned off when it's running at 850 revolutions per minute. It turns 1,250 revolutions before it comes to a stop. What was the fan's angular acceleration? How long did it take for the fan to come to a stop? Again, I need to assume it's constant angular acceleration to use these angular kinematics equations. just like we did with our linear kinematics equations. All right, so let's convert. I'm going to take 850 revolutions per minute, and I'm going to take 1250 revolutions. And I'm going to say that 1 revolution is 2 pi radians. And I'm going to say 1 minute is 60 seconds. I'm going to use my calculator. And I'm going to have 850 times 2 times pi divided by 60 gives me 89. And 1250 times 2 pi is going to give me 7,854. All right, so in my chart, my initial angular velocity is this 89. And my final angular velocity is 0. I don't know my acceleration. I do know my theta minus theta naught, which I'm saying is 7,854 radians or 2,500 pi radians. I can get acceleration with the v squared equals v naught squared plus 2a x minus x naught. So I'm going to rewrite this as omega squared equals omega naught squared plus 2 alpha theta minus theta naught. And I'm going to get alpha by itself. So I'm going to have omega squared minus omega naught squared divided by 2 times theta minus theta naught is equal to alpha. And so this is going to be 0 minus 89 squared over 2 times 7854. So I'll plug this into my calculator. And I have, sorry about that, negative 0.5 radians per second squared. And now I can solve for time in a number of different ways. I'm going to pick the v equals v naught plus at to get time. And I'm going to erase some of this stuff to make my life easier. Substitute in my rotational, and that tells me that omega equals omega naught plus at. And so I would have omega minus omega naught over alpha is equal to t. My final is 0. My initial is 89. And my angular acceleration is 0.5 radians per second squared. And so this is just going to be 89 times 2. 178 seconds. All right, I'm going to clear the ink. And here is the work. And again, I thought it'd be useful for you to see me do it step by step in the video. I know I'm going to show this to you guys, but you'll be able to find it on my YouTube channel as well. All right.